Joseph Fourier, he who invented the heat equation, who now will follow in his footsteps.
Alright guys, as you can see, I have this picture of this turkey that I drew on the upper left hand corner here. We're going to load this into Python, we're going to put her in the oven, and then we're going to cook it up. And we're going to see how long it takes to cook. And you'll be surprised looking at the center. So, there's a number of packages today. Obviously NumPy, Matplotlib. We're going to use scikit-image like we used in the previous video. And NUMBA is going to be used for all the numerical heavy duty stuff. So the heat equation is pretty simple. It looks like this. You have a Laplacian, U, and the partial derivative of U with T. U is temperature. Again, we want to solve for temperature. Alpha is something called the thermal diffusivity. It depends on the material. And T is time. So I looked up alpha for the turkey ahead of time. It exists. And so in 2 dimensions, in discrete form, right, if you have a grid of points, instead of having a continuous 2D place, again, we're solving this in 2 dimensions. We have a grid of points in 2D, and then this M, the upper thing, represents time, right? And I, J are the X and Y locations on that grid. So you can imagine that, evolving through time, you have basically like snapshots of the turkey getting warmer and warmer and warmer. So M is like what snapshot that is, and I, J are the coordinates here. And so you can write it like this. And if you want to like evolve that through time, right? You'll notice there's only one M plus 1 and a bunch of M's, so you can rearrange this for M plus 1, and then every point here in the M plus 1th time, so the next snapshot, depends on points of the previous time, and then you could just sort of iterate through that to get all your snapshots throughout all time. So let's first define our grid. I'm going to say edge is equal to np.linspace, and it's 100 by 100 image, so 0, 1, 100. And I'm going to make a mesh grid as well. So I explain this every video. You have a mesh grid of XV and YV. You have your 2D grid. XV tells you where you are in X, so it's repeated across columns, and YV tells you where you are in Y, so it's repeated across rows. There's an image I'll put above. So we have those two, our mesh grid. Now let's load the image. So image, we're going to use our libraries, is read, and the name of the file. And it needs to be in output. And so this is just a little error, doesn't really matter. So now we have our image, it's 100 by 100. And because images are stored reverse, I'm going to flip it. This just flips the y-axis, so it's not upside down. Sometimes there's this issue with things turning upside down. And now we can plot our image. And you should see, sure enough, we have our beautiful looking turkey breast that we drew. And so now what we can do is we say when we update the heat equation, this yellow, which is the oven temperature, remains constant, and we're just going to update the temperatures of the turkey, and the heat is slowly going to leak in. So now we want to get only the points where the turkey exists, right? When we update, we're only going to update the turkey points. We're not going to update the oven. The oven's at a constant temperature. We're only going to apply this iteration formula to the turkey points, and the oven will remain constant at each snapshot. So to do this is actually really simple. I'm going to create a Boolean array called turkey bool, and it's where image is less than 0.9. So outside here, it's all these points are equal to 1, and then these are darker. So if I only take the points where it's less than 0.9, I have a 2D array of trues and falses. Again, look at the image above for clarity. And it's just a bunch of trues and falses, so that's fine. Now we need to define the thermal diffusivity of the turkey, which I've approximated to be about 1.32 times 10 to the negative 7. And this is the units. If you look up here at this formula, you can determine what the units are, and the units are meters squared per second. So that's our alpha turkey. Now let's define the oven and the initial temperature. So the raw turkey temperature is going to be, well, I'm going to convert everything to Kelvin, so 273.15, which is 0 degrees Celsius, plus 25. So this is 25 degrees Celsius, or whatever this is, Kelvin. And then there's also going to be the oven temperature, which I'm going to say we preheat the oven to about 162, let's say 165 Fahrenheit. So now we have our oven temperature. So now we're going to set the turkey to be the initial turkey heat and the oven to be the initial oven temperature. So I'm going to define this initial heat array. Start it with zeros, and it's going to be 100 by 100. And our initial heat, where the turkey exists, right, is the raw turkey temperature. Right? And so I'm also going to set this to be the oven temperature. So this creates an array of where everything is the oven temperature, and then I say, okay, take where the turkey is, because I have those trues and falses, and set it to be the raw turkey temperature. And I need to make sure this is init heat. So now we have that array, and we can plot, just make sure that everything worked. I can make sure this is all good. And sure enough, it's hotter outside here than it is in the turkey. By the way, this is different than this. This is the pixels of the image. This is the initial heat of the turkey. So this is all good. And now we're going to define how many times we're going to update, because we need to iterate over and over so the turkey gets warmer and warmer. So we'll define those times. So to iterate, get warmer. And then we're going to only take snapshots every few frames, right? It'll update. We'll take a picture, update, take a picture, update. And we're going to choose 10. So every 10 updates, it takes a picture. If we take a picture every update, there's too much, right? It'll take up too much memory on the computer. So we can't do that. So there's going to be, I'm going to say there's times equals 360,000 or 36,000. So that's how many iterations we're going to have. And I'm only going to take 3,600 pictures. So F, which is the number of pictures we take, is going to be times divided by times snapshot. Sorry, times snapshot is how many pictures we take, and F is the interval, right? So if I take 3,600 pictures and there's 36,000 iterations, I'm taking a picture every 10 snapshots, right? And now we'll define our heat frames. So we're going to define like a photo album. So there's a 2D array, and there's going to be many 2D arrays, and this represents the heat at every time. So heat frames, and again, I'll just initialize it for now. And I'll say, so we're going to have times snapshot. So this is our photo album of every time we take a picture of the turkey being cooked. And it's 100 by 100. So it's a 3D array. So you have a picture, and then a picture stacked on top, picture. And we can create an animation by looping through these pictures. And we'll make sure that our initial heat frames is equal to our initial heat. Right? It'll be this. And then it will iterate. We'll iterate through this, and we'll update these. Right now they're equal to 0. But soon they'll be updated more and more. So the dimensions of this problem, you know, from this, I'm going to say this is about, from here to here, is about 50 centimeters. So that means our turkey is about 40 centimeters or so big. So x is equal to 0.5. Remember, everything is in standard units. That means dx is equal to 0.5 divided by 100. And dt is equal to 1. So we're doing 1 second. So note what this means. If we're doing 1 second, 36,000 means we're doing 10 hours. Remember, 60 seconds per minute, 60 minutes per hour. So 3,600 seconds per hour. So 36,000 seconds per 10 hours, because dt is equal to 1. So we're going to simulate the turkey cooking for 10 hours. right? And so now we need to compute this quantity S. And S needs to be less than 1/4, or otherwise this iteration algorithm will diverge and we won't get the correct solution. So let's just make sure that everything is good. So we have a Turk times dt divided by dx squared. And yes, we are less than 1/4, so we're good. And now I have my NUMBA function. This is a little bit complicated, so I'll go through it, but I didn't want to type it all out. So remember what we're doing is we have a picture of the turkey, a photo of the turkey at a time. And using this photo, we're going to get the next picture of the turkey. And it'll be a little bit warmer. And then we'll get the next, and the next, and the next. So at each time, we're going to go through that, and that gives us our next picture. The heat is slowly creeping in. So what do? Well, we loop through all the times, right? We're going to start with the first, then the second, then the third. And what I do is I define something called current state. Current state is the current picture we're looking at, right? And then I define something called new state. And new state is a copy of the current picture, right? And then looping through I and J, I update the new state. So new state gets updated based on this formula here. So that new state, the heat creeps in a little bit. So that's what I'm doing here. I'm saying new state is the current state plus all this stuff. That's that formula. So I make a copy of this, and then I update it, right? And then I do the same thing over. I copy this, and then I update it, and then I copy this, and then I update it, and I go, and I build up my photo album of these pictures of this turkey. And then this little thing here says, and then at the very end of this, I say my current state is my new state. So I start here, I copy my new state, I update it, and then this becomes my current state. And then I do the same thing, boom, 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 boom. Update it that way. It takes some time to read this code and understand it. And then I say if t modulo f is equal to 0, in other words, if I'm every 10th snapshot, remember we're updating it 10 times, and then we take a picture. So I take a picture every 10th snapshot, and I add it to the heat map, right? So this is my photo album. My heat map is my photo album of these pictures, right? So hopefully that makes sense. And so I can run this, and we get our function, and now we can solve it. So heat frames equals solve heat frames, and it needs to take in. So how does it work, right? Well, I told you we're only applying this formula here for the turkey pixels, right? So in this image, there's turkey pixels. I don't want to update the outside. I'm only updating the turkey pixels. So in this function here, I also say if it's the turkey, then I update. But if not, don't do anything, because outside of the turkey, nothing is changing. And so it takes in the initial, blank things. It takes in a bool, and this Boolean array tells you, is it a turkey or is it not? And only for the turkey IJ pixels do I update it. So I have my heat frames. I could solve this. It solves it very quickly. I'm going to convert back to Celsius. So heat frames minus equals 273.15 with an underscore here. And now I can make, for example, a heat plot of the final heat map of the final snapshot. So what does my turkey look like after 10 hours? What does the heat look like? So let's get a heat map. I'm going to call it Inferno because Inferno, of course, looks good for cooking. Plot.figure, and I'll make a fig size is 8 by 8. And we'll make a little. So we'll take the last one, heat frames -1. Remember, -1 is the final index in the array. 100 contours, and CMap is my CMap. And then we'll create a vmin and vmax. So vmin is equal to raw turk temp. I think that's how I have it. Nope, it's like this. Raw turk temp minus 273.15. We're converting degrees Celsius. And vmax equals oven temp minus 273.15. And we'll add a color bar. And here's our plot. So at the very end, our turkey is, warm, right? The middle of the turkey is about 103 degrees Celsius. If I, early on, if I take, say, the 1000th frame or something, right, the turkey is still warming up. So this is earlier on. We can make an animation of this turkey. So Here we have our photo album of our turkey getting warmer and warmer and warmer. And I can run this. Okay, so the animation has finished running. And you'll see, just to be clear, I pick a frame I. This is how Animate works. Again, look into this if you're curious. I just make a contour plot of 10 times the current frame number. So I have 3,600 pictures, but then again, I'm only taking the every 10th frame, right? So I update every frame, right? And when I save it to my photo album, I only take every 10th one. And then when I make the animation, just so that there's enough frames, from those every 10, I only take every 10th. So in terms of iteration updates, I'm taking every 100th update. So I'm taking every 10th and then every 10th again. So every 100th. And so each frame corresponds to 100 seconds. And I'm making 30 frames per second, right, in my animation. So that corresponds to 3,000 seconds. So each second on the animation, right, looking at this GIF, corresponds to just under an hour. So we're speeding up by a factor of 3,000 of normal time. So this is obviously going a lot faster than what you would normally see, but as you can see, the turkey slowly starts to bake, and it gets warmer and warmer on the inside, but it takes a while, and the outside, of course, is the hottest part, which you would expect. So this is nice, and we can examine a few interesting quantities just to finish up here. Let's look at what the average temperature of the turkey is, and also the coldest part of the turkey, because when you cook something, you want to make sure that the minimum temperature gets to a minimum limit, right? So that, there's no raw food or anything. So make an array of times between 0 and 10 hours, and it's the length of heat frames. And now I'll define something called average temp. So this is the average temperature. So I have my photo album of snapshots of the turkey. I'm going to take the average temperature of each snapshot. So np.array heat frame. So we're only selecting the parts of the turkey, right? We only want to look at the turkey. And we're going to take the mean. This. So this gives me my average temperature, and I'll do the same for the minimum and the standard deviation of the temperatures. So this will call it min temperature, and this I'll call standard deviation of the temperatures. And I made a little mistake. I need to add some square brackets here. Here we are. And this is the average temperature of the turkey versus time, and it increases almost logarithmically looking. So add a label for that. And then we can also plot the minimum temperature of the turkey. And it's interesting to compare these two. And we'll add a... Now, a lot of guides I was seeing said that the turkey should be at least 80 degrees Celsius at the minimum point. So add a little horizontal line there at 80 degrees Celsius. And as you can see, right, so this is degrees Celsius and this is time in hours. So I've added the label, the axis labels as well. As you can see, the average turkey reaches that 80 degrees very quickly, but the turkey minimum temperature of the turkey, it takes a long time for that to reach that 80 degrees limit. So that's why it takes a long time if you put a big thing in the oven for it to heat up. Now here's an interesting thing, and I'm going to add a grid here as well. Right, you see how long it takes, and that's because the turkey's whole and the heat has to seep its way through. But what happens if we cut the turkey in two? How much faster will it cook? So just to confirm, it takes up about 6.5 hours for the turkey to, the minimum temperature of the turkey to reach that temperature you want it to. Well, let's say we cut the turkey in half, right? And this can be done as follows. We'll say that turkey bool in the middle equals false. Well, what does this do? Right? If I rerun this code, look at this. You see in the middle, it's split. So it's like the turkey is in two halves, right? And we can simulate this again. Right? So it's simulated. Now, what happens if we do this again, right? So you saw here when it was in 1, it took 6.5 hours. I cut the turkey in 2, and look at this, watch this orange curve for this minimum to reach that point. And now it only takes 3.5, or around 3 hours for it to reach that point. So cutting in half, splitting the turkey in 2 cooks it much, much faster. So chefs, I don't know if you're watching, but science. In fact, I don't even know if you'd want to do that necessarily, but you know, if you're hungry and you want your turkey to cook fast, cut it in half. That might be really gross. Anyways, I'll end it off there today, guys. Hope you enjoyed. Remember to subscribe and like. Thank you.